Our final Gilbreth lecturer for today and our closer is Dr. Karma Sawyer. Karma is the division director overseeing electricity infrastructure and buildings at Pacific Northwest National Laboratory, PNNL. She is responsible for shaping and managing a vision and strategy to ensure that the laboratory addresses the Department of Energy's most important challenges in energy efficiency, clean energy, and electricity infrastructure. She has worked collaboratively with the national laboratories and external stakeholders to advance cross-cutting initiatives such as grid interactive efficient buildings, advanced building construction, and grid modernization. Please welcome Karma, who will discuss equitable building decarbonization through electrification. Karma.
Well, hello, everyone. I have to say it is an honor to be here today. I'm usually not a person who gets nervous, but being a closer for this group of speakers is quite a tough position to be in. I'm excited, though, to talk to you about this problem today. It's a problem, like all of my colleagues, that really needs the next generation of engineers. And I was inspired by one of the last things that Bo said in his presentation, which is that in engineering, it's really about people, and that is absolutely true for the problem of decarbonization. And so I'm eager to hear some ideas from you all how we could potentially address it. So, climate change. It poses a significant risk to virtually all human and natural systems, either directly or indirectly. And reducing greenhouse gases that are driving climate change are going to require sharp reductions in coal, natural gas, and oils, and large increases in renewable energy. And that transformation alone is a formidable engineering and societal challenge, but it is already happening. But virtually all of those energy systems are sensitive to the environmental changes from the climate, and on a lot of different timescales. These decarbonized energy systems like solar and wind and hydro, they are that much more sensitive. They are intermittent, and as a result, the energy supply could become less stable. And we are managing that. There are talented engineers out there right now whose job it is to figure this stuff out. Several of them work for me. But as our energy system transitions and as the climate changes, oftentimes people will feel those changes in their homes and in their buildings. That's going to be the front line. And there's increasing awareness that these impacts, both in the energy system transition and in climate change, they are not experienced equally by all people in society. The reality is that people have very different needs from their energy system. So elderly and disabled people, they use energy in different ways. They have different vulnerability profiles. So, I see that in my own household. I have an 11-year-old son with a severe disability. He uses an iPad for his communication. So if he is not able to charge that device, he cannot communicate his basic needs to people outside of his immediate family. That is not typical, but his right to communicate is a real thing that the energy system has to be able to deliver. Low-income households, we see in the news all the time, they spend a higher percentage of their bills on energy than affluent households. That can be a factor of 3 and 5. We're looking at people. We heard about the crisis in Ukraine and the impact not having natural gas is having on people's livelihoods. So I just finished telling you about how this clean energy transition is already happening. But in reality, that is true, but it's not quite that simple. Black majority census tracts have installed 69% less rooftop solar than no majority tracts of exact same household incomes. Since 2006, 90% of electric vehicle home income credits were received by the top income quintile. And only about 10% of people that live with multiple disabilities have access to paratransit. They live in paratransit deserts. They cannot get around. The engineering community needs to grapple with the fact that there is a foundational gap in understanding what these gaps are in equitable access to our energy system. Engineers need to recognize the needs of people by their demographics, by their age, by their race, their health, their poverty levels, understand the interactions of those needs, how they might compound or be cumulative over time. And then those technologies in the clean energy system, they will need to be designed to be safer and to support people's well-being across the entire life cycle. And engineers will also need to recognize the procedural limitations of energy system decision-making, because often that is what actually impacts what is in people's buildings. Energy equity is a relatively new concept. Certainly it's new to engineers, but it recognizes that disadvantaged communities have been historically marginalized and overburdened by pollution and underinvestment in clean energy technologies. They do not have access historically to energy-efficient housing or energy-efficient transportation. And an equitable energy system is one in which the economic, the health, and the social benefits of participating in all levels of those benefits extend to all levels of society, regardless of someone's ability, their race, or their socioeconomic status. And achieving energy equity requires that engineers intentionally design systems and technologies and procedures and policies that will lead to the fair and the just distribution of benefits in the energy system. And it is only through the goal of achieving energy equity that we can actually possibly achieve our societal goal of full decarbonization, because that requires that these technologies reach all people. That is a very lofty and challenging goal. So the federal government not only has a goal to fully decarbonize by 2050, but they've laid out a strategy to do it that in many cases is technologically feasible. It's built upon three principles. The first is that you decarbonize electricity and the energy supply. The second is that you use electrification and energy efficiency to decarbonize end uses. So that means you're electrifying your cars, your buildings, and the industrial sector. And then finally, for the sake of completeness around this strategy, I will not talk about this. It is to enhance the carbon storage potential in natural systems. So I will be talking about that central pillar, specifically the decarbonization of buildings. It is a critically important sector for decarbonization, and it is much more challenging than people realize. The Rhodium Group has done an analysis to show that, I didn't realize I went ahead. Sorry. The Rhodium Group has done an analysis to show that in 2022, our emissions went up in the United States by 1.3%, and that is the second year in the row that has happened. In the electric power system, the energy supply has actually had emissions go down. It's outside of the power sector where emissions have gone up. And the single biggest area where emissions have gone up is directly using fossil fuel in buildings. That's combustion in homes. So your heating systems, your water heating systems. That went up by 6%. It is the only sector that went up to pre-pandemic levels. So the building sector is very, very important for that reason. It's important to our decarbonization agenda, but it is also important to the human experience. Americans spend 90% of their time indoors. 75% of our electricity is used in buildings. It accounts for 36% of our CO2 emissions. Americans consume more primary energy in buildings than any other sector, including transportation. It's in buildings. And if you look at that energy in that pie chart, you see that 55% of it is electricity. That's a lot, but it's that other 45% that is coming from combusting something in your home. That's your decarbonization opportunity. So that combustion in homes, it's important for other reasons too. So we've all seen this in the news. I'm not going to talk about gas stoves today, although if you want to talk about gas stoves, we can talk about that in Q&A. But combustion in homes is really important from a decarbonization perspective, but also because of the impacts it has on people's health. People who are susceptible to the adverse impacts of pollution, the very young, the very old, people with cardiovascular disease, they spend more time indoors than the average person. And the indoor concentration of pollutants is 2 to 5 times higher than what you see in outdoor conditions. Combustion indoors produces gases like carbon monoxide, produces particulate matter that will impact the development and the worsening of asthma. And there's a disproportionate burden in asthma rates in the US, particularly amongst children. African American children and children of Puerto Rican descent have a disproportionately higher asthma rate compared to their peers that are white, from other Hispanic groups or Asian. And that's even after scientists have eliminated the influence of other variables. It really is important to the human well-being. And so because of that decarbonization work, because of the impacts for people's health, heat pumps, that is what I'm going to talk about today, not gas stoves, heat pumps. Heat pumps are having a moment. I've worked in building technologies for a lot of years, and I cannot believe how much excitement there is around the modest heat pump technology. So if you go onto YouTube, you'll see that this nonprofit, Rewiring America, recently did a campaign called Mr. Heat Pump Goes to DC. Check it out. It's fun. They go and they talk to the director of the Office of Science and Technology and Policy, Sally Benson. They talk to senators. But heat pumps are really important and they're really exciting. Heat pumps can deliver efficient heating and cooling to your home, both heating and cooling. And when they're properly installed, they can provide 3 times more heat energy than electrical energy they can consume. They are highly energy efficient. And this is possible because heat is being transferred rather than converted from a fuel like it is in a combustion heating system. Air source heat pumps are not new. They have been used for many years in nearly all parts of the United States, except in areas that experience extended periods of sub-freezing temperatures in the very cold climates. But recently, because of engineers, there have been advances in this technology, and cold climate heat pumps now provide a legitimate space heating alternative in these cold regions. And that is an incredibly big deal. In 2022, not for the first time, because 2020 was an anomaly, but in 2022, heat pump sales exceeded gas furnace sales. And this is very, very meaningful to achieving those decarbonization goals. A recent study in energy policy by researchers at UC Davis, they showed the first detailed emissions forecast for operating either a heat pump or a gas furnace in residential heating in homes across the US for 15 years. And they showed that if you go everywhere from the generation source down to the buildings where these pieces of equipment are operated, and you count for all the different emissions that come from that system, you can get a 53 to 67% reduction in a 20-year global warming potential over that, and those emission savings are going to increase over time. That range depends on a lot of things. Old homes, those are great ones to replace. There are huge emissions opportunities, savings opportunities there. It's also really important in regions like the Pacific Northwest, where there's a lot of clean electricity. You see that more and more here in California. And you see it globally too. The International Energy Agency estimates that an air source heat pump can supply 90% of the global space and water heating needs with lower CO2 emissions than gas boilers. So if you look at this map, it's those green and the blue regions, that's where you can have 50 to 100% emission savings opportunities by using a heat pump. And so I am super excited about heat pumps. They really are incredibly important. And very few people know what they are, but I really believe that you will. You'll know it when you're homeowners, you'll know it as engineers. But that's actually, I think, not the right question to ask. Because the right question to ask is how heat pump deployment actually impacts people's lives, individual people's lives. What does it look like in communities? So come with me to rural Alaska, to a small community called Cordova. So this is a beautiful picture of Cordova. Right now, home heating in Cordova, Alaska is provided primarily by heating oil. But the local utility has a goal to decarbonize, and cold climate heat pumps are at the center of their strategy. The community also has this large commercial fishery. That is the economic engine of this community, and it is a large load for electricity in that community. So as I said, Cordova is in rural Alaska. It is so isolated that the microgrid that utility owns, it's member-owned, it's not connected to any other lines or any other community. So all those homes need to be heated, and that fishery needs to stay going for the economic well-being of that community. So my colleague, whose picture's up on this slide, Sam Rosenberg, he's doing a research study about how cold climate heat pumps are going to work for this community when they're paired with advanced controls that can shift loads from a time where there's a lot of demand on that system to a time where there's less, and whether these technologies can actually deliver for the people in Cordova. Still underway. We're collecting data right now. I love the example in Cordova because it highlights the central role that decarbonized buildings can play in people's economic well-being and their health impacts and many other things. But for the case of deploying heat pumps in communities like Cordova, it's really important that we understand those community needs. And it goes beyond what we might traditionally think about as the energy system. In reality, when we're talking about electrifying buildings and installing heat pumps, we get the biggest bang for our buck, I said earlier, if we go to retrofitting old buildings. That is really hard, it can be slow, and requires a lot of money up front. Most heat pump demonstrations are not like the one I just showed you in Cordova. They are in affluent communities. So we do not know how this technology will work in communities like Cordova. That's why we're up there. But in reality, in a lot of buildings, especially in ones that are underserved, they don't have proper insulation. So if you put that heat pump in there and you promise you will save people money with this energy efficient technology, if you don't have a well-insulated building, that money will not come back to people. You will not be able to follow through with that. And what's worse, in those underserved communities that would benefit most from some of the health impact savings and the economic savings that could potentially come from heat pumps, they could also be affected by an unreliable energy system and an expensive power grid. The grid is really, really important to people's well-being. In fact, I would argue that grid planning is probably one of the most important things that we as engineers working in this space need to understand if we want to have an equitable energy system. Historically, grid planning has worked around the objectives of providing safe, reliable, and affordable electricity to the customers. Those are those items there in blue. People know how to manage to those objectives. They've done it for years. But now we have new objectives, the ones in orange: decarbonization, resilience to extreme weather, and equity. And it's these emerging objectives that are critical to consider when we're reimagining a paradigm around threats to our power system. The threat could be climate change. The threat could be cyber attacks. The threat could be inequality, depends on the community that you're in. And each of those threats require a proactive response. So we have a research team led by Bethel Tarakenke. She's focused on understanding specifically this most emerging objective of equity. Very few people who work in power plants or in power grid planning understand energy equity. And she's working to understand how customers or categories of customers will be affected differently, and how we can plan our grid and our system accordingly so that the system will equitably distribute the benefits and also the burdens of services provided by the power grid. We're working really closely with the people that are actually making decisions on how to engineer the power grid. We're helping them understand what the right metrics are. And really the most important thing to those decision makers is to understand the trade-offs between these different variables. So usually what we show them is something that looks like that spider graph down here with each of those objectives, and we have multiple different scenarios. I'm not going to show you a lot of spider graphs, but I wanted you to have a sense of what they're actually looking like, the people that are making decisions on the ground when they're trying to figure out what a community will look like. So I'm going to take a little bit of a detour here and make sure everyone knows enough about the power grid to understand some of the analysis we've done around these systems. So this is a map of the North American transmission grid. We've got the Western Interconnect that's in red. Blue is the Eastern Interconnect, and ERCOT is down there in Texas. So I said this is transmission. You'll hear me talk about transmission and also distribution. Those refer to the different stages of carrying electricity over poles and wires to homes and businesses. And the primary distinction between the two is the voltage level that the electricity moves at. So you can think of the transmission system as being like an interstate highway. It moves a lot of electricity, bulk electricity, over long distances at very high voltages to substations that are closer to the demand for the electricity, like people's homes and their businesses. So you'd probably recognize transmission lines as these very, very large towers and poles that carry huge number of wires. Transmission lines typically move more than 100 kilovolts or so and above. So once those high from the transmission lines actually get reduced or stepped down to transformers, that's when they get sent through distribution lines to people's homes and to their businesses. So what I'm showing you here, this box, this is a prototypical feeder that we developed. It's an example. So it's a 300-node feeder that represents a suburban area, large suburban area on the West Coast. We have 5.3 megawatts here. It serves 380 residential customers and 12 commercial customers. We have identified 2 disadvantaged communities in this analysis. We labeled them as DAC1 and DAC2. So that this means that there are 130 customers that are in a disadvantaged community and 250 that are not. So we are not using the specific demographics of the community here to be able to determine whether or not they're disadvantaged. There are a lot of privacy issues that made that difficult in this project. So in this case, what we did is we assumed that DAC1 was disadvantaged because it's far away from the substation. The substation is down at the bottom there. Because it's far away from the substation, it just has a much less favorable profile for voltage. This is just a characteristic of a feeder, and it's much more susceptible to there being resilience challenges, having some sort of damage happen and your power would go out in a community that's far away. DAC2 has a smaller load. So the houses are smaller there. So we just make an assumption based on those physical characteristics of the feeder that these are disadvantaged communities for the purposes of understanding these trade-offs. So the first thing we did is a really simplified analysis to show which locations on this example feeder would be suitable for solar. And this was basically just due to where there would be voltage violations. So we'd go over voltage. This is called identifying the solar hosting capacity. And it showed that, as predicted, DAC1, which is far away from the substation, would have these resilience and these high voltage challenges, and it would not be suitable to solar. So that community could not have solar unless there were upgrades made to the system. It's instead the non-disadvantaged community, shown in green, where you would see solar, favorable solar installations. And this is based purely on the physical property of the feeder. So as I said earlier, disadvantaged communities adopt technologies in different ways than non-disadvantaged communities. A great example of that is electric vehicles. So I'm using electric vehicles here in this study. It could also be true for heat pumps. Those are just large electric loads. So in 2022, electric vehicles adoption, what do you think it is in non-disadvantaged communities, in affluent communities? What percentage of cars are EVs? Any guesses? 25%. So knowing that, 25%, I'm showing you the data's on here. So what do you think it is in disadvantaged communities? By 5%, that's right. So we're assuming there's a 25% difference. So that's just baseline. Remember, I'm just giving you some of the assumptions about what adoption will look like over time for this technology. The other thing that you know is that your base load is smaller in disadvantaged communities. Homes are smaller. They're conditioning less space. And they don't grow as quickly because they're not adopting these advanced technologies. So this is the assumption that we're making here around base loads. The base load is going to be smaller for disadvantaged communities, and it's not going to rise as quickly. So what we did is we did an analysis for each year starting in 2024 to identify where there would be thermal violations in the transformer and the line conductors due to bringing on more electric vehicles. So we could use a business as usual assumption which I just showed you, that disadvantaged communities have less load to begin with and the load doesn't rise as quickly. And if you do that, you get these red dots. And all the upgrades in the system would be in the non-disadvantaged region, all of them. But if instead you change the way you did your assumption and you added the objective of having equity, you started to see the green dot, which is because they were getting more electric vehicles, they had a need for an upgrade in the system, and there was value given to an upgrade in that system. But that happened by 2026, it continues into 2028, and into 2030. So what this analysis showed us that is if we do our planning with these business as usual assumptions, where we just need to provide affordable, safe, and reliable electricity without thinking about equity, all of the upgrades would go to the non-disadvantaged communities. They wouldn't need to put in technologies that would prevent those overvoltage violations. They wouldn't need to upgrade their assets for the new heat pumps or the new electric vehicles that would come online. That would be, those upgrades would, if they took place, would be limited to the non-disadvantaged communities. The disadvantaged communities don't get anything unless you intentionally build them into your system. And if that's the case, their lines are upgraded. They get voltage mitigation solutions. Things change. And they get the new clean energy technologies delivering reliable service to their homes and to their businesses. But the other thing that means is that if you include equity, it's going to cost more. It's going to cost more upfront. And that is not the way the utilities have been planning. Over time, they're trying to reduce costs. But if you pay those costs, because you value equity, these communities get financial benefits, they get health benefits, they get resilience benefits. But remember, these are the trade-offs the decision makers are trying to make. How do I think about equity knowing that the cost will be higher? How do I think about resilience knowing that the cost will be higher, and where is the resilience going to be the most impactful to avoid? So if I had a different feeder, remember, I just use this as an example, and different definitions of a disadvantaged community, we would have different solutions. So think about that community in Cordova, Alaska, that has the acute fishery, that has all these new heat pumps coming online. You need to understand all those things when you're doing these analyses. And every community is going to look different. And so you have to have engineers that not only can solve these technical problems, but are talking to people. And they're understanding what their needs are. And they're thinking about how you make these hard decisions and how you advise decision makers based on all of these factors. It's critical that we take the time to do all that. So in closing, I want to ask you all to think that way, to think about people when you're solving problems. Think about the considerations you need to make when you're looking at any new technology. I mean, I want you all to work on heat pumps, but I mean, that's just me. It's going to be important for clean energy technologies and for all the other technologies that people are thinking about too, to ask those hard questions. I really do believe that heat pumps are going to improve people's lives. They're going to improve people's health outcomes. They're going to decarbonize our energy system. I don't know how much and I don't know when, but I believe in heat pumps. But I also believe that none of those positive impacts are going to reach underserved communities if we don't work in partnership with them, and we don't talk to them, and we don't listen to them, and perform really equity-aware engineering analyses around grid planning, around community operations, and think deeply about how these things work together. And engineers are also going to need to develop the next generation of technologies, because the majority of technologies, when you look into climate change analyses that'll fully solve our decarbonization problem, they don't exist today. And so we need to be developing and deploying these technologies in a way that really understands and respects communities' goals for their energy system, and for all types of communities, not just the ones we're familiar with, particularly those that have been marginalized and underserved. Thank you.
Hi.
Hi.
I'm Noah. I'm a sophomore at Samuel Academy. And my question is there other reasons why these disadvantaged communities are overlooked other than their financial situation?
I mean, I think the short answer is yes, and I'm not going to claim to be an expert on that. I mean, I really don't know all the answers for it. I mean, I think there are large systemic reasons. I mean, some of them are geographic, right? They're physically far away. Oh, sorry. They're physically far away from where the energy system infrastructure is. Some of it is, I mean, some of it is systemic racism. Some of it is financial. I think all those things play together. I mean, they're intersectional connections. And actually, I would add that we don't actually, from the perspective of the energy system, we don't even know how you would define a disadvantaged community. And we just published this paper, and asked people to give us feedback on how, from the perspective of the energy system, we should do that definition. So I'm giving you my own opinion, based partially as a professional and partially as a citizen, but I think that's a great question, and it's one that people are debating right now in the field. I hope that helps, Noah.
I'm Kara Coulter. I am a junior at Cabrillo High School. How have different ethnic or racial backgrounds been affected by fossil fuels in homes? Has there been a significant difference between one community and another?
Yeah, absolutely. So the asthma rate data I showed you is at least partially tied to combustion in homes and particulate matter in homes. The detailed connection to that, I think, is still being researched in a pretty significant way. I said I wasn't going to talk about stoves, and I really don't know that much about gas stoves. That's part of the reason for it. But one of the things that I have read is that what happens in homes with gas stoves very often is that they don't have proper insulation. So on very cold nights, people actually use their stove and their oven to heat the space, and that's when you get a lot of particulate matter coming into buildings. A lot of that happens in communities that have been underserved, whose housing is not energy efficient, and have been marginalized from the broader energy system. And there are also issues with things like siting refineries and transportation systems and how transportation lines are laid to run through communities so that there are pollutions from cars that can impact people's health and well-being as well. But these are very complicated issues that are still being addressed.
Hi, again, I'm Carl from Cabrillo High School, a senior. There's without a doubt that there's benefits to electrification, but in regards to electric vehicles, how do you ensure that electrification is done in a sustainable and reliable manner, especially in regards to the lithium mining operations and their damaging effects to the environment?
Yeah, that's a great question. And I'm hoping, I might say I don't know to some aspect of everyone's question. I was telling the other presenters earlier, the best lesson I got from my dad professionally was to always say you don't know when you don't know. And I do not know the answer to your question. But I do know people are looking into it because it is a real challenge, both geopolitically and environmentally. There are a lot of advanced battery technologies that material scientists are looking into right now to be able to address exactly that issue. I don't know how that will shake out. I'm not an expert in battery chemistry. But I think we'll need to weigh those pros and cons over time, and it could easily change as electric vehicle technology evolves and is more utilized.
Hi, my name is Heaven Rojas from Samuel Academy, and I was just wondering, how did you get into your kind of field of work?
I'm sorry, will you repeat that?
How did you get into your kind of field of work?
Oh gosh, there's a lot of luck that came into this for me. So I am actually a chemist by training. I spent a lot of time in the lab through my PhD, and I transitioned to mechanical engineering as a postdoc. I spent a lot of time studying heat transfer at that point, and heat and mass transfer are really critically important to understanding how building science works, how insulation can work, how different particulate matter and gases can flow through buildings. And I had a lot of, I'll say guts for lack of a better word, to try things that I had no technical experience in. And I was willing to not know a lot for a very long time. I think those are some of the best career decisions that I made. If I could go back and do it again, I would have studied buildings from day one. I love the work, but it's not how it happened for me. I didn't know that this was a career. And so if you want to know how to be a building scientist, go into mechanical engineering would be my first answer. But I don't think that needs to be what limits you. I think if you follow your heart and you take advantage of opportunities that sound interesting, even if you're scared, you're going to go to good places.
Hi, my name's Michael. I go to Cabrillo High School. I'm a junior. I was wondering, instead of electrical cars or EV cars, hydrogen cars are now coming out. Would that also be better in benefiting the emissions?
It depends on where you get your hydrogen from, right? Just like electricity, a lot of it comes down to, and the lithium battery question, right? A lot of it comes down to your source of your materials or your energy. So potentially yes, potentially no. Ultimately, if you want carbon-free electricity, if you want carbon-free hydrogen, you need a lot of carbon-free electricity, and that's going to have significant impacts on the amount of electricity generation you need as well. The energy system is super complex. It might not be as complex as we are, per some of the stuff Caitlin said earlier, but it's pretty complex and interrelated. And so the answer is almost always, it depends. And in that case, I feel confident that that's the right answer.
Hi, Andrew Percussion here again, but senior at Cabrillo. But can we use like alternate to like batteries, like nuclear batteries on like electric vehicles?
Like nuclear, the batteries, the nuclear would be on the vehicle or on the power grid?
Anyway.
Either, yeah. So there are a lot of alternative battery chemistries that are being evaluated right now. It's going to come down to cost, right? I mean, the batteries we have right now have been engineered for cost reductions, and the cars themselves have been engineered to be able to get to the point that we are right now. Adding a new chemistry in can really change that significantly. And it's not to say that it could not be displaced, but it would change the auto industry quite a bit to change the battery chemistry as well. So over time, yes, I think we've got the batteries that we have right now for a while. Lithium-ion will be with us for a little while.
Okay, one last question. We have a question.
My name is Adrian, senior at Cabrillo High School. And since the push to EV and lack of gas-powered like things like cars and all of them, do you think the U.S. power grid will be able to accept the demand it's going to happen eventually?
We need a lot more transmission. Not today's grid. We need a lot of transmission. Transmission is really hard to site and really hard to get online. I think we need more flexible grid technologies at the distribution level and throughout. We need a wartime effort to be able to meet our decarbonization goals that have been set up by the federal government. And a lot of that comes down to grid infrastructure. And the legislation that has been passed recently is going to make a huge dent in that. But we need to move really, really quickly. I have a lot of actual anxiety around some of these equity problems because having these conversations and engaging with communities, it's not fast and it shouldn't be. But our climate crisis is here right now. And so I don't know how to weigh those trade-offs. I spent a lot of time thinking and worrying about it. And that issue, though, that you brought up around the readiness of the power grid, we better get ready.
Okay. Thank you. Let's thank Norma again. Thank you very much. Very good. Karma, you illustrate two principles we should follow as engineers. One is to not only do great things, but do good things, right? Great and good. And secondly, engineering now, as we move forward, really needs to work with social sciences to figure out what the right things are to do and how to handle different situations in communities. So thank you for reminding us of that. It's very good.